They hardly matter. Okay, have you got it?
Yes, sir.
Okay. AZ is given by this expression. AZ nearly equal to why AZ, because current is in the Z direction. So A also has to be in the direction of current. There are no other vectors here. Only current is the vector. So AZ is also a vector. Since the current is in the Z direction, you have A equal to Z, AZ cap of AZ. So AZ component only is present. Okay, like point source only, except for this, everything like for the whatever you have discussed for point source. In point source, we took capital R and small r same because it was located at the origin. The point source was located at point source means I mean infinitesimal dipole. L is less than or equal to lambda by 50. Okay, I go to the next slide. So AZ far field region. So this one. I is nothing but I of Z dash because X dash Y and Y dash are 0. Okay. So e to the power of minus j k r by r. Okay. And this is like this. Capital R becomes small r. So it is, you can this is a constant, small r. You can take outside the integration sign because if you vary Z dash from minus L by to capital, small r doesn't change. Small r doesn't change. So e to the small r can be taken outside the integration. Mu e by e to the power of minus j k r by 4 pi r I z dash e to the power of k z dash cos theta d z dash. Till here, have you understood fully? Till here?
Yes, sir.
Is it okay? Okay. Good. Next slide. I'll go to the next slide. So, if you take don't consider integration for a point source, diz will give d theta. Okay, iz dz dash will give d theta. If you don't, in the previous slide, if you don't consider this integration, only then you get daz, and for that daz you have dA theta, dE theta. Sorry, are you getting it? dE theta, j eta k iz dash e to the power of 4 pi r sin theta. How did we get this sin theta? See, if it is for a point source, you have seen the derivation of e theta for a point source, and it is like this. Derivation for e theta for a point source is like this. Have you got it? Derivation of e theta for a point source. Point source means infinitesimal dipole, that is L less than lambda by 50, less than or equal to lambda by 50. We have seen this derivation in the last class for a point source. You can go through it. So this is for a point, diz dash in this case is taken as a point source or an infinitesimal dipole. Okay, so dz dash. So so dE theta you have. So DER is 0. This all are 0. We have seen this. We have seen this. These things are all 0. Okay. So DH5 will be 1 by eta of this. 1 by eta. I is equal to V by R. This is like V. This is like I. So V by R. Eta will be divided by eta. So JKIE Z dash e to the power of minus JKR by 4 pi R sin theta dz dash. Have you understood till here? Any questions? This we have seen, all these things are 0. For a faraway point, all these things are 0. E5 was 0, ER will be 0 for faraway point, and HR will be 0 for faraway point. The H theta was 0 because H was only in the phi direction. So DH5 is given by this expression. Any questions?
No, sir.
Okay. Letting R is equal to R minus Z dash cos theta for phi terms, and R is nearly equal to R for amplitude terms. We go to the next slide. So dE theta will be of this form. Okay. So and it is like this. So if you substitute for capital R, it is here. So this is sine theta because of the this thing point source. We have seen that where the electric field is a proportional to sine theta. Okay, so that is coming here. So dz dash. So if you want to get E theta, you have to integrate between minus L by 2 plus L by 2 d theta. So this is called the element factor and this is called the space factor. Now here, what we do is we consider different points z dash from minus L by 2 plus L by 2 and do this integration. This only z dash is a variable here. Z dash. Okay. Other things are constant. Theta is also constant. Theta is also constant because theta is from the origin. Theta is the angle with respect to the origin. Or since our capital R and small r are parallel, so theta is also constant. So pattern multiplication of total field is element factor into space factor. Can I go to the next slide?
Yes, sir.
Yeah, thank you. So we have current distribution. Now we'll current distribution. What I will IE? IE will be given by AZ dash I naught sine KL by 2 minus Z dash. You have seen the sine curve like this for dipole antenna, finite length dipole. Okay, so it is I naught KL by K into. So if you substitute Z dash is equal to 0, what you will get? I naught sine K L by 2, this also both will converge. If you substitute Z dash is equal to 0, both will converge. Both will give the same. If Z dash is equal to, in this equation, Z dash is equal to L by 2, this will be 0. Naturally, at the end, the current should be 0. At the end point, current should be 0. So this equation is all right. So this is also fine. If you substitute Z dash is equal to minus L by 2, this will be 0. So this is equation is fine. Okay, can I go to the next slide?
Yes, sir.
Yeah. Now you see, you do this. Let us substitute in that this thing, whatever I current in the that integration for E theta. So here these terms are constant. So I naught into sine KL by 2. So this expression. Now we have this. This is of this form. So the integration is taking of this is of this form. Okay, this is a. So you can use this for solving this integration. Where alpha is plus minus j cos theta, beta is plus or minus k, and gamma is KL by 2. So if you use that, you will get E theta in this manner. So E theta is C into this one. This is the field pattern of the field. You C is a constant. It is like same in all angles. C is a constant. It is same in all direction. So this contributes for the pattern. Okay. So H phi is given by nearly equal to E theta by eta. C is equal to J theta I naught e to the power of minus jkr by 2 pi r. Okay, is it understood?
Yes, sir.
Okay, thank you. So could we use the equation for far field radiation here? Okay, we can use C in the for the point source. So C this is given by C. H phi is E theta nearly equal to E theta by eta. Okay, next slide. So WAV is half into real part of E cross H star. Okay, so it is a theta component E theta and a phi component H phi. So it is AR cap real part of E theta H square. This is WAV. WAV means average power density. AR into E theta by eta. So AR, so you get this expression. So WAV, you get this expression. WAV. Is it okay?
Yes, sir.
Yeah. So WAV W is the W rate is given by this expression. U is given, U rate is given by R square W rate. U is the radiation intensity, R square WAV. So this is B naught called B naught. So this is the pattern. This is the pattern pattern. So this is the power pattern U rate. This contributes for the, this is a constant given by this. So I naught, if you treat it as constant, if you, it will be I naught. This is at the current maximum. I naught is the maximum value of current. So you have, so this form here E phi is 0, E phi is 0. So you have this P rate is to R square W rate, D theta is given by 4 pi U theta phi by P rate, and UN of theta phi is U of theta phi by U max. Any questions on this? Any questions?
No, sir.
Okay. So you have U of theta phi is eta in the F of theta, where F of theta is given by this U of theta phi. So it is max U of theta phi. Theta is equal to 0. Theta is equal to 0 phi. Theta is equal to pi. For theta is equal to 0 and theta is equal to pi, pattern is 0. Okay. So radiation intensity along dipole axis is 0. Along dipole axis is 0. Radiation intensity. Okay. So this is the pattern for sinusoidal pattern. Sinusoidal time distribution for different lengths. L is less than or equal to lambda, lambda by 4, lambda by 2, 3, lambda by 4. L is much less than lambda, lambda by 4, lambda by 2, 3, lambda by 4, and lambda. Lambda. See here, you can see different values of our beam width. If L is less than or equal to lambda, the beam width is very less. So for the higher, longer length, the beam width will be less. For shorter lengths, beam for the infinitesimal dipole, half hour beam width will be 90 degrees. Sin theta, infinitesimal dipole means sin theta. Sin theta will be having HPBW. Sin squared theta. Current power distribution. Amplitude pattern. So yeah, sin theta has 90 degrees. HPBW has sin theta has 90 degrees. So L lambda by 2 has 74.3 90 degrees and L less than or equal to lambda has 47. This is how do you get it from this equation? From the previous equation, you have to just substitute values for theta and get the, so make the plot. You have to give values for theta and make the plot. So for lambda with 90 degrees is greater than or equal to HPBW and is greater than or equal to 47.8 degrees. Okay. So we'll go to the next slide. So with what we see here is with the higher length, larger length, the pattern is more directional. With larger length, pattern is more directional. With the shorter length, pattern becomes more less pointed. Hello, yes. So have you understood? Can I go to the next slide?
Excuse me, sir. Can you go to the previous slide?
Yes. Yeah.
In this, when we said that theta is 0, we get a 0 by 0 form. So how did we just
0 by 0 form? We can use L-Hospital's rule. No, you know that.
I see, sir. Got it, sir.
Okay. So here, if the pattern is more than L, 1 lambda, you have more than one more than you get different more number of loops. The pattern, if the length of the antenna increases beyond lambda, it will have more number of loops.
So your voice is not clear again, sir.
Voice is not clear.
Yes, sir. It's slightly getting distorted. I'm not able to hear.
So if length of matter is more than 1 lambda, you get minor lobes. You get minor lobes. L is here. L is equal to 1.25 lambda. You got one minor lobe here like this, like this. Okay. So if till L is equal to lambda, we had only one major lobe. We had only one lobe, major lobe, and one back lobe. But when L is equal to 1.25 lambda, how do we get this? Basically, you keep on assigning values. You just substitute the value of L and theta. Keep on assigning values to theta and plot the pattern. Have you got it? Hello?
Yes, sir.
Yeah, thank you. So here, this is two-dimensional pattern for L is equal to 1.25 lambda. There is nothing much to explain in this slide. I'll go to the next slide. Okay, P rate, you know this equation. You have seen n number of times. Okay, okay, and this is this U rate sin theta, the U of theta phi sin theta d theta d phi. Okay, you know this. So P rate half I naught square RR, and RR is 2 P rate by I naught square. I naught is what is I naught? The maximum value of current on the length of the dipole. Maximum value of current on the length of the dipole. It's not the input current, that's the input lead. It need not be at the input lead. Input lead, I will be equal to I naught only if it is lambda by 2. Length of the dipole antenna is lambda by 2. If the lambda by 2 antenna, the input current will be maximum. So I naught will be equal to I in. Here, for a finite length dipole, I naught is the current where the I naught is the point where current is maximum. I naught, maximum value of current. So RR is 2 period by I naught square. You know this. So what was missing in that expression? The time variation. Always, every equation has to be multiplied by e to the power of j omega t. We are not showing this because it is common to all equations of electric field and magnetic field. So we are not explicitly showing. It doesn't mean that it is not a function of time. It's also a function of time. I hope I have been telling you this again and again. I think you know this. So here he has made the comparison for infinitesimal dipole. The directivity is 1.5, and for lambda, it's 2. L is equal to lambda 2.411. So in dB, it is like this. So in terms of half power beamwidth, it is like this. So which is better actually? So which is better antenna? Infinitesimal dipole or a finite light dipole? L is equal to lambda.
Finite net.
Yeah, L is equal to lambda is much better than infinite because both ways it is having better performance. Here also it is 3.822 dB higher than this, and here also it is less than this. Okay, I'll go to the next slide. So again, radiation resistance. We have derived the expression for radiation resistance for finite length dipole 80 pi square L by lambda or something like that, whole square or something. So if you substitute that for L is equal to lambda by 50, you get 0.003, and for L is equal to lambda, you get 199. So which is better? This is better because radiation resistance is higher, more number of more power is radiated. Higher RR is too better. Input resistance RN. We will see this later. We are not come across this, and it is between this and this limit. For L is equal to lambda is shown as infinity. We can't have input impedance infinity, but it will be very large. We'll see that later. It is going to come again later on. So ideal current distribution, we have already seen this. I don't have to explain. So the current distribution is like this. The I naught is at this point, I naught, maximum current. This is I in. I in. So this is the for finite length. This is L is greater than lambda by 2. Can you make out that L is greater than lambda by 2? Can you make out that L is greater than lambda by 2 for this? But less than lambda. This current distribution is L is greater than lambda by 2, but less than lambda. Can you make out?
Yes, sir.
Yeah, good. If you can make out that, it's very good. So we have P rate is equal to half I naught square RR. We have defined it like that, P rate. So it is, if you take the input point, at I naught, the radiation resistance is RR. At I in, the resistance will be something R in. So if you equate these two, you get like this. R in is equal to RR. So if I in is equal to I naught, then R in will be RR. That is for lambda by 2 dipole only. I in will be equal to I naught for lambda by 2 dipole. R in is equal to RR if for half wave dipole, lambda by 2 dipole. So in other, if it is not lambda by 2, then I Z dash is equal to 0. I in is I in. Z dash is equal to 0, and from the current equation we have this. For Z dash is equal to 0, you get this. Z dash. So if you substitute here, you get the expression for. I'll go to the next slide. Can I go to the next slide? Hello? Hello? Can I go to the next slide?
Yes, sir.
Okay. Rin is given by this relation. Rin is at I in and RR is at I naught. So Rin is a relation between Rin and RR is this. So for when L is equal to lambda, Rin will be infinity. But practically it cannot be infinity. Current not be nearly equal 0, but it will be very less value. So R will be high for L is equal to lambda. L is equal to lambda. So this is L is equal to lambda by 2, R is equal to RR, L is equal to lambda, R is equal to infinity. They assume sinusoidal current is pretty zero current at input terminals and hence infinite input resistance for dipole of length equal to integer multiples of wavelength. In reality, the current is not zero in this case due to the finite feed gap and the finite radius of the wire. Next, we will come to half wavelength dipole. Any questions till now?
Sir.
Yeah, thank you. Half wavelength dipole L is equal to lambda by 2. So we will use the general equation for finite length dipole and substitute L is equal to lambda by 2. We'll use the general equation for finite length dipole d theta L is equal to lambda by 2. You get this equation. L is you substitute the expression for in the expression for d theta for finite length dipole, you get this equation. And h phi is d theta by eta, you get this. Current in the z direction, so the it says bad network quality. So can you hear me?
Just barely, sir.
Yeah, I am also getting that message. Network is not good.
So your voice is breaking at times, so it's hard to hear, sir. It's hard to hear, so you can't hear it properly.
So, but you can manage, no, somehow. Instead
So,
of having
no, sir, because it happens in this class only mostly, sir. So when you're saying the main point, it gets cut off, so it's hard to listen to it. Even if I put the volume high up, it's getting distorted, sir. So it's difficult.
okay, till now you are managing, no? Now, currently.
So I said earlier also, but I don't know. It's hard to manage, sir.
So let us see whether it improves in due course during this presentation. See, have you got this E theta and H5 for L is equal to lambda by 2? Hello? 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 Hello?
Yes, sir.
Okay, thank you. I don't know. No. You can see the slide, no? It is not, I am not able to see the slide.
Yes, sir. We can see the slide.
Something went wrong with this. Okay. WAV is given by this. Okay, WAV half into E theta square by eta. Half into E theta, magnitude of E theta square by eta. So that is WAV, and that is given by this expression. So this is nearly equal to sine cube theta. Okay, this one is nearly equal to sine cube theta. So U is equal to R square WAV. So eta I naught 80 pi square. So this is the expression for power pattern. Is it fine?
Yes, sir.
Thank you. So P rate is you integrate this thing U of U sine theta d phi. So you get this, you have this form. Now this one, it is not easy to integrate. You have to use numerical methods of integration. Have you heard of numerical methods of integration? Simpson's rule, trapezoidal rule. Hello? Hello? Have you heard the Simpson's rule and trapezoidal rule like that?
Yes,
In
sir.
mathematics? Yeah.
We studied Runge Kutta, sir.
What is that?
We studied RK4 method also, sir.
Okay. If you use any of those methods, you will get this integration value like this, 2.435. See, it is given like this, sin of 2 pi. Now this one is called sin of 2 pi. So that is 2.405, 435. So if you substitute that, you get, I think I missed one. D naught is 4 pi U max by P rate. Theta is equal to pi by 2, U is maximum. So this one 2.435 here, 4 by 2.435, get 1.643. So it is better infinitesimal dipole where it is 1.5. So for half wavelength dipole is 1.643. Okay. And AEM is lambda square by 4 pi to D naught. So you get this. And RR is 73.05 ohms. So this is a very important derivation. you have to get this value exactly 73.05 ohms, and that is for half wavelength dipole. That is for half wavelength dipole. 73.05 ohms. Can I go to the next slide?
Yes, sir.
So J, now for the standard antennas, the reactance is 42.45 ohms. 73 ohms is what is RR, what we got for lambda by 2 dipole. J for lambda by 2 antenna, it may not be, we may just say lambda by 2 antenna, dipole antenna, and we may not give this value, but you have to know, use this value. 73 plus 4 J 42.5 ohm may not be given in the problem. They may say lambda by 2 dipole. So you have to take Z in as 73 plus J 42.5. Okay, very important. So here he has compared infinitesimal dipole, E theta C1 sine theta, and U is C2 sine square theta power pattern. For lambda by 2 dipole, C1 dash into, this is the field pattern, and U is the square of this. So it's nearly equal to sine cube theta. Can I go to the next slide?
Yes, sir.
So the pattern of lambda by 2 dipole is like this. Pattern of, if you plot, how do you get this pattern? You have to keep on assigning values to theta. You have to keep on assigning values to theta from theta equal to 0 to pi. Pi is it is not independent. It is not a function of pi. So you get this pattern. And this is a two-dimensional pattern, comparing it with isotropic source. Isotropic source. So isotropic. So D, this thing RR is 73.1 ohms and D naught is 2.15 dB. We have seen this 1.64. We have already come across this. Okay, and this is 73 ohms RR, and RR is equal to R in for half wavelength dipole. RR is equal to R in, because I naught is at the input point maximum. I naught I is equal to I naught at input point. So I naught is equal to I in. Okay, next. Is it understood?
Yes, sir.
So far, our derivations has been on the basis that antenna is isolated. There is no other surface near it. There is no other body near it. So it is in isolated region. That will not be the case always in reality, because there is a ground surface. Now, if the ground surface is taken into account, what will be the effect on the pattern? We will see that now. So first we'll see vertical polarization. Here you can see an antenna. So this is the reflecting surface, like Earth surface, a perfect reflecting surface. Okay. Now an antenna is mounted at a height h. It's an infinitesimal dipole. So don't see this part below this. I'll tell you later. Okay. Now, if this is the point of observation, there will be two rays. One is the direct ray and one is the reflected ray from here. Now, the electric field at this point P1 is the vector addition of this direct ray and the reflected ray. Electric field at point P1 is the vector addition of that electric field due to direct ray and due to the reflected ray. So, any point you take, electric field is the vector addition of direct ray and reflected ray. Now, to account for reflected ray, we consider an image source. That means we take that the reflected ray is coming from an image source, image source. This is the image source. Okay. Now here you can see the direction of current is in the positive z direction. Now how do I decide the direction of current of the image source? Okay. How do you consider the direction of the image source? Is you have to satisfy the boundary condition. You have to satisfy the boundary condition. Boundary condition requires that tangential component of electric field around the boundary on the boundary is zero. Tangential component of electric field on the boundary is zero. How do we ascertain the direction of image current? See here, if you see the direct ray, the direction of electric field is in the E theta direction. That is perpendicular to this side like this, E theta direction. So similarly here, reflected ray has to be in this direction. The other the path, this path will have electric field in this direction. So if the tangential component of the electric field has to be zero, the reflected ray should have electric field in this direction. If electric field in this direction, so only then tangential component of electric field will be zero in the boundary. So how do we ascertain that? See here, you draw two mutually perpendicular vectors. Okay, one parallel to the boundary and one normal to the boundary. So the parallel component should cancel out here. So if you want to have reflected ray like this, then the image source should be also like this, because the electric field of the image source should be in this direction. So image current also should be in this direction, directly to the positive side. Have you understood this? Have you understood this?
Yes, sir.
Very good. Thank you. Good. If you want to consider the reflecting surface, then you can remove the reflecting surface and keep an image current. If you keep an image current, you can remove the reflecting surface. So it is like an array. The problem is now turns out to be an array, two elements, two antennas. And array is a combination of more than one antenna. So you have an antenna array. One is the direct actual source, one is the image source. So there are two rays. So the total electric field is the vector addition of electric field from the direct source and from the reflected source, from the image source. So you can ignore this part. If you consider that, you can ignore this. You can see one ray like this, one ray like this. Have you understood this point?
Yes, sir.
So what decides the direction of the image current is the boundary condition. What decides the direction of image current is the boundary condition. So if the boundary condition has to be satisfied, direction of image current will be like this. This is for an electric current source, electric current. Okay, not magnetic current. Here, so that is what he has explained. See here, boundary conditions getting cancelled off. Boundary conditions being satisfied. The tangential component of electric field getting cancelled off. Two components, normal component and horizontal component and vertical component. This is opposite to this. This is opposite to this. So it cancels off. So this is the antenna mounted at a height edge. So the direct observation point, you have the direct ray and the ray. So if you ignore the image, the reflecting surface, you have to treat the image source. Okay. And what will be the limits of theta here? What will be the limits of theta?
Sir, 0 to pi by 2.
Yeah, 0 to pi by 2. Beyond theta is equal to pi by 2, this electric field is 0. Beyond theta is equal to pi by 2, electric field is 0 because this is a reflecting surface. Okay, earth surface, below the earth surface, the electric field is 0. Here we are treating that the sigma is infinity, a perfectly conducting earth. So based on the boundary conditions, we can decide what is the image current. So if the electric field is like this, current is like this, electric current, then the image current should be electric current should also be in this direction. If the electric current, if for horizontal antennas, horizontal antenna. If the electric current is like this, image current will be like this. That is to say, just how we decide this is by understanding the boundary condition. So we have to satisfy the boundary condition. What needs to be done to satisfy the boundary condition? For magnetic current, it is like this: vertical current, vertical antenna, and it is like this. For horizontal, both will be in the same direction. So this is only decided by the boundary condition. Sorry. I made a mistake. I think. Yeah. I think so. Slide is repeating. Now, if it is magnetic conductor, okay, that is for electric conductor. Magnetic conductor is like this. You don't have to worry about this magnetic conductor. For this information is given here. So now we'll see vertical electric dipole. Vertical electric means electric current. Source is electric current, not magnetic current. Vertical magnetic dipole, if it is like, then it is magnetic current source. Here, vertical electric dipole. So here, you see the image. Now see here, R1, this is R, this is R2. Have you followed this slide? Have you followed this? R1, R, with respect to R, it is theta, with respect to R1, it is theta 1, with respect to R2, it is theta 2. And psi, what is shown here is psi, it is 90 minus theta. It's not important now. So, have you understood this slide?
Yes, sir.
Now, if it is a faraway point, what changes we can make? If it is a faraway point, we can make R1, R and R2 parallel. If it is faraway point, far field radiation. So E theta direct is given by this expression. It is an infinitesimal vertical dipole. Okay, infinitesimal vertical dipole. So E theta 1 direct. This is a standard notation for finite length dipole. Sorry, infinitesimal dipole antenna. This is the standard expression. We have already derived this. So that's why I said you have to memorize this result. You are going to straight away like this. If you don't know this, if you are not knowing this, then you will fail. You will not be able to continue further. So you have to remember this expression. This is a very important expression. It keeps coming again and again. This is for a point source or infinitesimal dipole. The E theta. Okay. So it is like this. E theta reflected. So it is RV reflecting coefficient. Okay. Reflecting coefficient. Now here it is +1 because the direct ray and reflected ray is the image current. The direct current and image currents are in the same direction. So +1. Okay. So +1 is in the opposite direction. It will be -1. Okay. Image current also in the same direction. So J eta. So reflection coefficient RB is +1 for the reflected ray. J eta k I naught e to the power minus j k r by 2 4 pi r 2 sin theta 2. So E theta total is E theta direct plus E theta reflected. Have you got it?
Yes, sir.
Thank you very much. So here, so now we'll see, take these lines as parallel. We'll see, take a faraway point. We are making an error, but otherwise our life will be very miserable. We don't make this approximation. Okay. So with this, it will be very much simplified. With this will be very much simplified. We'll make like this. Then in that case, so this is H. This is also H. Below the image current is below Z. Below Z is equal to 0. H, the height is H below the reflecting surface. R1 is equal to, so this one, so R1 can be written as, if they are parallel, R1 can be written as R minus H cos theta. Can you understand this? The lines are parallel, so theta is same. Theta 1 is equal to theta 2 is equal to theta. So R1 can be equal to R1 minus H cos theta. R is much greater than H. That is for far fields. Far fields. Have you got it?
Yes, sir.
Okay, thank you. So R2 is equal to R plus H cos theta. For R greater than H, R much greater than H means far fields. So R2 is equal to R plus H cos theta. So far field approximation for phase terms, R1 is equal to R minus H cos theta, R2 is equal to R plus H cos theta. And for amplitude terms, R1 is nearly equal to R2 is nearly equal to R. Theta 1 is equal to nearly equal to theta 2 is nearly equal to theta. Any questions? Any questions? Can I go to the next slide?
Yes, sir.
So E theta so if you add E theta direct and E theta reflected above Z is equal to 0, you get this expression. Can you derive this and see now whether you are getting this? E to the power of jk R1. R1 you substitute R minus H cos theta and R2 you substitute R plus H cos theta. You do like this and you expand E to the power of jk R1 and jk R2. You add them. You will get 2 cos theta. And E theta is equal to 0 for Z less than 0. Have you got it?
Yes, sir.
Okay. So this is called the element factor. So element factor is as if that infinitesimal dipole is at the center without any reflecting surface. Element factor is like the pattern of infinitesimal dipole at the center, at the face center of the array. At the face center of the array. Okay. And this is the element factor. And this is the array factor. This is because of the two isotropic source, and this is the factor due to two isotropic source. Isotropic source, what is the pattern? Isotropic source, e to the power of minus jk R1 and e to the power of minus jk R2. If you add them, you get 2 cos k cos theta. So this is for an infinitesimal dipole, element factor. This is combination of two isotropic source, array factor, combination of electric field due to two isotropic source. Very important. Are you getting it? What is the pattern of isotropic source? E to the power of jk R1 and e to the power of jk R2. That is the pattern. Amplitude factor, whatever it is, e to the power of jk R1 and e to the power of jk R2. Now, if you add that, those two, you get 2 squares cos k cos theta. Have you understood this?
Yes, sir.
Now the element factor is for infinitesimal dipole placed at the face center of the array. Face center is, that is the z is equal to z dash is equal to 0 point. So this is the face center. You get the element factor. Now this is for factor, like two isotropic source placed at a distance of 2h between each other. E theta is equal to 0 for z is equal to less than or equal to 0. Because reflecting surface, we have reflecting surface at z is equal to 0. below that, z is equal to 0 and below. So the pattern would look like this. Now, what does this pattern dependent on h? Basically, it depends on h and theta. H and theta. You can see here. You can see the previous slide. What are, these things are constant. Theta is constant. J is constant. I naught is constant. L is constant. Theta and h it depends on. So the pattern looks like this for different values of h. So now you see here there is an antenna and there is an aircraft coming near the antenna. There is a direct ray and a reflected ray. Now, when the aircraft is far away, sometimes it may be able to hear better reception than when it is near, because there can be nulls based on the nulls. Although the aircraft may be near, it may not have a very good reception of the signal, because there is, in that direction there may be a null. So even it doesn't mean that the aircraft is far away, the signal strength is weak, and aircraft is near, signal strength is better. No, it depends on the nulls. Okay, so so he has to switch to a different frequency when he gets a null point. He has to shift it to a different frequency. You can see there are many nulls. See, in this direction there is a null. Here there is a null. So many nulls are there. So in this direction he will not get a very good signal. So here, although here in this direction he may get a better signal. Okay. So that's what is here. So vertical dipole, number of dipoles, you don't have to bother about this slide. Okay. So P rate is WAV into DF, W rate AR R square sin theta d theta d phi. So it is pi integration limit is 0 to pi by 2. Integration limit 0 to pi by 2. Very important. Okay. So P rate is given by this expression. So it is this one. Have you got it? Y sin cube theta. Here. Have you got it? Y sin cube theta here.
Yes, sir. That is the expression for a finite.
Yeah, infinitesimal dipole. Sin square theta into sin theta is here for the this sin theta. Sin cube becomes sin cube theta, and this was there cos space cos theta. So it was cos square space cos theta. So period. This integration turns out to be like this. You don't have to do this integration. You should need to memorize this, but okay, it will be of this form. Okay, this integration will be like this. The result of this integration is this. Any questions?
No,
Any
sir.
questions? Okay. So P rate is 2 eta, so like this, R square sin theta, so it is given like this. So that was period only last in the, so here. So here U is equal to R square WAD R square to 1 by 2 eta theta square. We are getting this. Sin square theta into cos square cos theta. So any questions? Can I continue? Hello, can I continue?
Yes, sir.
So U R square WAV R square by 2 eta. So use this case, you get this. So D naught is U max 4 by U max by P rate. So you get this. U max theta is equal to pi by 2. At theta is equal to pi by 2, this becomes 1. So this also becomes 1. Sin theta will be 1, and this part also will be 1. So U max is this. So D naught is equal to 2 by. These expressions are very important. You can have a numerical based on these equations. Period and your D naught, both. From the period, it's easy to find D naught because period is being used here, expression for period. RR 2 period by I naught square. So you get this form. L by lambda square into. Okay. So again, this is an important formula which you have to remember. So this is being summarized here. Whatever we discussed, it has been summarized here. So D naught 4 pi U max by period, and RR is 2 period by naught square. So okay. So you can skip this side. Not a don't have to bother about this. The power pattern. So if you so directivity and resistance, radiation resistance depends on the height of the antenna. Height. So it is like this. From here, it is almost constant. It's like this. Its height above the infinite. After L is equal to lambda by 50, infinite dipole. Can I go to the next slide?
Yes, sir.
Okay. So maximum occurs when kh is equal to this thing 2.881 and h is equal to 0.54585 lambda, d naught is equal to 6.566. And you could see from the previous slide 6.566 here. So it is only 8.173 dB. Monopoles and dipoles. Monopoles and dipoles are widely used antennas in wireless communication systems. Monopole are particularly popular for portable units on automobiles and other vehicles. In practice, wide use is made for quarter wave length monopole. I'll show what is a monopole. So this is a monopole. You have half of the dipole, and you feed the current between the ground plane and the other one. This thing is there, no? Upper wire and the between the ground plane you feed the current. So it is half of the dipole. So if you are given problem of monopole, it is equivalent to a lambda by 4 monopole on a perfect electric conductor. So it is you consider a dipole and image current. You can treat that image current, and you can do the integration for P0 theta equal 0 to pi by 2. So below pi by 2 to pi, it will be 0. So Zin for half wave monopole is half into Zin of dipole. And D naught is 2 D naught in dipole. D naught of monopole. Any questions on this? Because
No,
P rate is half. P rate is half. Zin will be half of half this dipole. P rate is half of, and also P rate is half. So D naught will be 2 D naught. For monopole, D naught will be 2 D naught of dipole. Have you got this?
yes, sir.
So for monopole, if you are asked to find out, derive the equations, you can consider a dipole antenna. The bottom half will give the image current, and while integrating, you integrate between theta is equal to 0 to pi by 2. Okay, not theta is equal to 0 to pi. So you will get half the radiation power. So radiation resistance will be half, but at the same time directivity will be 2D naught of dipole, because the period is half of the period of dipole. Any questions? Have you got it?
Yes,
Hello, have
sir.
you got it? Okay, thank you. So Z in for this thing for monopole is 36.5 plus J 21.25. Both will be half, because the wire is half of that of dipole, wire length. So reactance also will be half. So this is for dipole, equivalent dipole. Z is 73 plus J 42.5 ohms. Dipole lambda by 4, lambda by 4. So linear mole especially are used for transmitting elements for wireless mobile telephone, cellular telephones, civilian bands, CB radio, cellular telephone, rooftop, automobile antenna, amateur radio antenna, and so on. To improve the radiation efficiency at these frequencies, radial wires or metallic discs are sometimes placed on the ground to simulate a perfectly conducting ground plane. Earth is not a perfectly ground plane or a reflecting conducting surface. So you put a metallic sheet at the bottom of the antenna to get a effect of a perfect conducting surface. Oh, sorry. So, okay, these are the different where we use this monopole. Okay. So next, horizontal polarization. That means if you place a antenna parallel to the reflecting surface. Again, there is a direct ray and a reflected ray. Direct ray and a reflected ray. So you have to take image current. Image current is decided based on the boundary relation. Tangential component of electric field is 0. So if you see, if the antenna is image current is like this only, in this direction only, the boundary conditions will be satisfied. If it is in the same direction, what happens? The electric field also will be like this, and it will add tangential component of electric field will not be 0. So this is for electric current source. For magnetic current source, it was in the same direction for horizontal dipole. For vertical dipole, it is in the opposite direction for magnetic current source, placed on a perfect electric conductor. So here again R1, R2, R, theta, theta 1 and theta 2. So for a faraway point, you can treat them as parallel, R1, R and R2. Have you got it?
Yes, sir.
Okay. Now the direct ray. Now he has not written as sin theta because in this case the angle is different. It is not in the vertical z-axis. So sin he has written as sin phi. Okay. Now what is phi? We can make out from this this thing. Phi is 90 minus theta. Phi is 90 minus theta. So it is phi. Okay. So here j eta k I naught d to the power of j minus j k r1 by 4 by r1 sin phi, and this thing is rx. This is here negative because the image currents are negative. Rx reflection coefficient is -1 here. Reflection coefficient is -1. So minus j eta k I naught L e to the power of minus j k r by 4 by r2 sin phi. Have you understood?
Yes, sir.
Okay. Now you have this relation AR is vector AR cap is given by this. Now AY cap dot AR cap is given by this cos psi is equal to cos psi. How do we do that? AY cap dot AR cap. AR cap is here, this is given here. So if you do the dot product, you get cos phi. Cos psi is equal to sin theta. So you know dot product is, you can see it is cos psi, and it is called sin theta sin phi. So sin psi will be plus or minus square root of 1 minus cos square phi minus 1 minus sin square theta. It is nothing but sin square theta sin square phi, because cos phi is given by this relation cos phi. Any questions? You can go through. I can give time if you want to go through. Have you understood?
Yes, sir.
So again, for far field approximations, R1 is nearly equal to R minus H cos theta. R2 is equal to nearly equal to R plus H cos theta. R1 is equal to R2 is equal to R theta 1 is equal to theta 2 is equal to theta. So E side direct. Now he has not called it as E theta because theta is not the actual the thing which is angle which is be considered to be psi. So E side total is equal to E side direct plus E side reflected. So you get this. So now here it becomes 2j sin kh cos theta. Array factor, this is the element pattern. Element pattern, this is the array factor. Now element pattern is for the, if you consider infinitesimal dipole at the that is equal to 0. Sorry, that is equal to 0. That is the element factor, because sin psi is represented by this sin psi. So, and this is like two isotropic point sources placed at above the reflecting surface and below the reflecting surface. So, isotropic point sources e to the power of minus jk r1 minus e to the power of minus jk r2. So, that will give 2j sin kh cos theta. So, is it fine?
Yes, sir.
So, this is the pattern at different edges, h height at different height. Again, pattern depends on h and theta. Three-D pattern. Okay. Lobes, you don't have to bother. See that. Lobes is 2h by number of lobes. Okay, now here, example 4.5. There is an infinitesimal dipole along the y-axis. Infinitesimal dipole. Here see infinitesimal dipole along the z-axis. Now there is an infinitesimal dipole placed at the origin. The direction of the current is in the y direction. How do we solve this? Now A is given by this. A theta is AY cos theta sin phi. If you get AY component, you can convert it to spherical components. Spherical components. How do you convert AY into AR, A theta, A phi? You know that. Okay. So A theta and A phi, since you are considering only far fields, you consider A theta and A phi, and E theta is from the far field equations. Far field equations which we discussed in the third chapter. E theta is nearly equal to minus j omega A theta, and E phi is nearly equal to minus j omega A phi. So this is the expression if infinitesimal dipole is oriented along the y-axis. Similarly, you can find it further if it is oriented along the x-axis. Same way you can find out. Is it okay? This is example 4.5 in the book. Hello?
Yes, sir, this is okay.
Radiation intensity of now this is u of theta phi. You know how to get r square into WAD, all those things you know. So you can this is how u of theta phi you have to get. Theta is between 0 to pi by 2. Maximum radiation intensity and the direction is a function of K. So here E rate is given by this. This you have to memorize. This you have to memorize. E rate is given by this expression. It is not easy to integrate this. So the result is given. So you memorize this. So RR is given by this 2 period by I naught square by this. Any questions? So you can have two types of pattern. Pattern here less than lambda by 4 and lambda by 4, less than lambda by 4 and greater than lambda by 4. So you can have two approximations like this. Okay. So for lambda by 2, this is not that important. You can also skip this if you want. So U max for lambda by 4 less than lambda by 4 and greater than lambda by 4. That's what is given here. And D naught for because pattern depends on H. Pattern depends on H. Here taken two scenarios. H less than or equal to lambda by 4 and H greater than or equal to lambda by 4. Okay. Directivity also H less than or equal to lambda by 4 and H greater than or equal. And this is the radiation resistance. Sorry. This is D naught, what is given here. And so you can ignore this. It is not required here. Here, tending to the limits for D naught is here given. It is 6 and 7. H is equal to 0. The D naught is he has given two limits. D naught KH tending to 0, 7.5 by 7 KH, KH whole square. And the higher KH tending to increase the directivity. So that is plotted in this curve. Like how we plot it for vertical dipole, horizontal dipole also D naught and RR is being plotted. So I will complete this fourth chapter by this, through this. So any questions on in the fourth chapter? Next class I will get the fifth chapter, loop antenna. So till now, if you have any questions, you can ask me. So the last part is not that important. You just need to memorize the expression for D naught and RR. Okay, and you have to derive the expression for E side, E side direct and E side reflected, adding them and all those things. Any questions?
No, sir.
So I will conclude this chapter 4 today. So next class I will we can discuss chapter 5, loop antennas. We have two more chapters left. Two more chapters. Sixth chapter is slightly long. So fifth chapter maybe we can complete in 2 hours. Okay, I'll take attendance now. Okay, you can leave this thing. It's not getting downloaded. Thank you.
Thank you, sir.
Thank you, sir.